Christina had a little box after the CTF correction, symmetry, determination of symmetry, and this is an old topic, so I look in my room and could find some old overheads, which maybe will be useful. We will see. So it's very important to determine the symmetry of your 2D crystals. And as you have all heard, an electron micrograph is a projection, to go to approximation, of the object along the direction of the electron beam. In other words, the image that we have is a projection image of the object. And so this is a two-dimensional object. And two-dimensional objects which are periodic can be described as two-dimensional plane groups. And there are 17 possibilities to arrange something in an object periodically in 2 dimensions. And these are listed in the international tables for X-ray crystallography at the beginning. So there are these 17 plane group symmetries, and then there are the 230 three-dimensional space groups. However, our 2D crystals are not really 2D objects. They have an extension also in the 3rd dimension, so they have a top and a bottom. This is a special case sort of between the 2D objects and the 3D objects. And such objects can be also described, or the symmetry properties of such objects in crystals can be described by the so-called two-sided plane groups. And there are, in general, 80 possibilities to arrange such objects in 2 dimensions. But for chiral molecules like proteins, there are only 17 possibilities to arrange these objects into two-sided plane groups. And this is a list of the two-sided plane groups, and the nomenclature here is in the left column, and the first letter here is a P or a C that defines if it's a primitive or a face-centered two-sided plane group. And then comes the symmetry operations, and in general, in electron microscopy, we like to have the first symmetry operation as the operation which is perpendicular to the plane of the crystal. So, for instance, we have the 2 here means a twofold rotation perpendicular to the plane of the crystal. It's possible now also to make a correspondence between the two-sided plane groups and the conventional three-dimensional space groups. So this list here also has a column for the corresponding three-dimensional space groups. And you can find information about these in the international tables. And also here are the projection symmetries. So these are the real 2D projection symmetries, which I mentioned are listed in the first section of the international tables. And this nomenclature goes back to a paper here by Holzer in 1958, and I heard Richard Henderson told me a couple of months ago when I met him that a Swedish guy was a postdoc in the lab of Richard Henderson in, I think, beginning of the 80s or something like that. And they, this guy from Sweden, Sven Hommöller, he's very interested in symmetry. He's now been working in material science. He's famous in Sweden now because his son, 12-year-old son, solved a very difficult problem in material science and quasi-crystal problem, which they had been working on for a couple of years. And just by playing around with overheads and things like that. And this guy with, any preconceived idea of what things are, he solved the problems. He's on the paper actually now, so this has been in the news in Sweden. But anyway, Sven was postdoc in Richard Henderson's lab, and they had worked out all the nomenclature and the properties of two-sided plane groups, and they were about to publish that and had a manuscript ready. But then they found out that it was already had already been published in, I think, Zeitschrift für Kristallographie or something like that in 1958. So at the end, it was just one sentence in another manuscript referring to this paper. So this may happen. Okay. So a little bit about crystals here also. Yeah. We've heard a lot about unit cells, and by definition, a unit cell is the smallest repeating unit in a crystal, and it's defined by the lattice vectors. So this is very simple. So this is my crystal. It's an Escher drawing of fish, different gray tones, but it's the same object. And you can already see that they have it's periodic and they have some kind of symmetry. So the first thing we can do is to define lattice points of this crystal. And in principle, these lattice points can be positioned anywhere. The only condition is that the distance here, the lattice vectors, should be of a certain value which is related to the crystal, and also the angle between them should be defined, of course, to the crystal. But in principle, you could put them anywhere. But I put them here at special positions, and that's due to the symmetry. So this is the unit cell, and now you can see that the lattice points are positioned here in the center of the unit cell. So if you sit here on a lattice point and look around, it will look exactly the same if you sit here or if you sit here, right? So that's the properties of the crystal. And the unit cell is defined by A and B and the angle between them. And it's obvious also when you look at this that these fishes are related by symmetry. So in this case, this white fish here is related to this one by a rotation along this line, rotation and the translation. So in 2D nomenclature, this is called a glide line, but in 3D, it corresponds to a screw axis along the B-axis. And the same thing is true for fishes in this direction. So this glide line also in the other direction. So when crystals have symmetry, then it's parts of the unit cells are related. So in this case, there is an asymmetric, I call this an asymmetric unit. So this is the smallest unique unit, which is then related to the other half of the unit cell here by this glide line. So there is two asymmetric units in this unit cell. So it was a while since I used this, and I think there's no glide line. It's not in this direction. It's not in this direction. It's only along the B-axis. So there are two halves of the unit cell which have the asymmetric unit related. So maybe I don't remember this, but maybe I used it as an example. One of the glide lines is correct and the other is not. Yeah. And this is then the asymmetric unit with this unit cell. So let's go then to a real structure example. So this is a projection map, and there are 4 molecules here in the unit cell. And first of all, the unit cell is has an angle of 90 degrees, but it's not quadratic, and you can see that if we put another one on top of it, unit cell axes are not exactly on the same length. And I know that for this particular protein, the A-axis is 91.9 and the B-axis is 90.83, so they differ a little bit. So it's not a square lattice. We can suspect that there is a twofold lattice here, perpendicular to the plane of the crystal, and by rotating 180 degrees and putting the other one on top of it, it's evident that the twofold axis is in the center, and it's also at the corners of this unit cell, with this unit cell symmetry. We can also suspect that, for instance, this unit here is related to this protein unit here by a glide line or a screw axis in this direction. And this is evident also when we take this one, turn it upside down, and translate it half a unit cell in this direction and get excellent correspondence. And in this case, of course, the correspondence is 100% because I've already imposed the symmetry on the projection. And in this case, it's also a twofold rotation along the other axis. In this case, we have glide lines in both directions. So in 3D terminology, then screw axis in both directions. So this would then correspond to a two-sided plane group symmetry, small p 2, 2, 1, 2, 1, and in 3D nomenclature, capital P 2, 2, 1, 2, 1, 2, 1. And in this, it would be worthwhile to mention also that electron microscopists likes to have the first symmetry operation first, or the symmetry operation perpendicular to the plane of the crystal first. So we call it P2, 2, 1, 2, 1. But if it would have been a 3D crystal in X-ray crystallography, it would have been P2, 1, 2, 1, 2. So there might be a difference between the nomenclature in EM and X-ray crystallography. So I also have this here, which is same protein, but it's a different crystal form. So this is an hexagonal crystal form. No, it's okay. I only want to look at this part. So this is the protein again. So in this case, there are only 2 protein units in the unit cell. So this is from the hexagonal crystal form then, and if we now compare with the orthorhombic crystal form, ones I showed previously, P2, 2, 1, 2, 1, there's a quite nice correspondence here of the asymmetric unit, the one protein unit. So these are from completely different experiments, so to say, completely different crystals. Okay. And I also have 3 other overheads which show something that you have encountered and which you also will do in the exercises, that is finding the lattices. And in this case, there are also 2 lattices, so we can find 1 lattice here. And then if you rotate almost 90 degrees, you can find the other spots, the other lattices. And in summary, so we have two lattices which are rotated almost by 90 degrees. So this is a tubular crystal with crystal orientations which are almost 90 degrees apart from each other. Okay, so let's switch back to the modern technology. So we have already seen now that depending on the symmetry, the unit cell may contain multiple copies of the molecule. So if we have a high symmetry, there will be more molecules in the unit cell. If there is no symmetry at all, it's a triclinic system. There's generally only one molecule in the unit cell. But in addition, there might be non-crystallographic symmetry that may add even more molecules to the unit cell. Actually, I think I should switch back to this one, because this is illustrated here. Because this protein, if you look at it, it seems to be close to have a threefold symmetry here in the center. And actually, this protein is a trimer. So but this symmetry operation here is non-crystallographic. And it can be very useful to apply this non-crystallographic symmetry during processing and during math determination. So non-crystallographic symmetry may add additional molecules to the unit cell. So in this particular case, instead of having 4 molecules in the unit cell, we have 12 in the unit cell due to the non-crystallographic symmetry. And this can be quite informative at a very early stage, actually, when one has obtained 2D crystals of a new protein, because if you determine the unit cell size, the lattice vectors and your angle, you determine the unit cell size, the area, and compare them to the molecular weight of your protein, it should be, this could give an indication of the oligomeric arrangement, because it turns out that for most, for membrane proteins which are rather hydrophobic, so that they don't have very large hydrophilic domains sticking out from the membrane. So if most of the mass is confined to the lipid bilayer, they generally have a packing density around 20 to 30 Dalton per square angstrom. So if you use that as a figure, you can determine corresponding oligomeric size, which fits to that packing density. Of course, if you have something which is very large sticking out, then it doesn't hold anymore. But for small membrane proteins, the packing density is normally 20 to 30 Dalton per square angstrom. So how to determine the symmetry? Well, we can look at the lattice parameters and the angle between them, and that will give some information, of course. And then one can calculate a map without any symmetry and get some ideas of what the symmetry might be. And in addition, we can go to the international tables and look at the phase relationships in the particular plane groups. So for instance, here they have PG, and PG corresponds to a two-sided plane group with a screw axis along one of the lattice vectors. PGG corresponds to two perpendicular screw axes, and if we are not sure if we have PG or PGG, for instance, in that case it's very easy, because here we have the information that all the phases should be 0 or 180. So these are the Fourier components here divided into the real and imaginary parts. So A is the real part, B is the imaginary part. So B equals 0 corresponds to a phase value of 0 or 180. So if we look at the phases, once we have moved our unit cell to the proper phase origin, and if the phases are very close to 0 or 180, it's very likely that it's PDD rather than PD, for instance. So this could be quite informative, and this has been applied in the program ArtSpace in the ML system, and which is also in 2DX. Here you feed in your data, your amplitude and phase values, and then you get a list of the phase residuals in the different symmetries here. So in this particular case, for instance, we see that we have a phase residual, let's say 52.5 for a two-sided ring group with a screw axis or rotational axis perpendicular to the plane of the crystal. And there are 17 comparisons for this phase residual here. And this, if it's a P2, it should have phases 0 and 180, and this is compared here in the phase residuals versus the theoretical possibilities of 0 and 180, with 45 degree will be the random value then, and here it's 26.3 for 34 comparisons, and this is the phase origin here, coordinates in the phase origin. And then there is a listing also here on the target residual based on statistics. So the program takes into account the quality of the data and combines this phase residual information into some kind of target residual here, and makes a comparison with the actual phase residual. And then it turns out that for this crystal, it's a very clear answer. So P12 with 2,1 with a 2,1 screw axis along the B axis has a very low phase residual here, both for the comparisons to other spots and for the theoretical comparison. So in this case, it's quite clear, and that is indicated then by 3 different indicators: acceptable, should be considered a possibility. This is a very clear case.
So
yep.
P3 has no theoretical target.
Yeah, because it doesn't have basis. And
there's no one constraint.
Yeah. Yeah. You can also, when you run ArtSpace, limit to, for instance, hexagonal lattices or to also rhombic lattices, so that you don't get a complete list.
Could you just say again what is theoretical?
The theoretical is the centered space group will have phases 0 or 180, and
centric applies as before.
Yeah. So and if you look at your phase values down, it measures the difference from either 0 or 180, and so in this case it's only 8.6, so it's very close. For these, it's only 4 spots here, so it's a very small number of spots. But these spots are very clearly.
What is the target?
It's a program. I don't know exactly how it's but it calculates. It takes into account the quality of your spots. I mean, your spots might be quite noisy, and then. So depending on your quality of your data, I think it makes sort of a combination of these 2 characteristics, and then makes a list here. Actually,
is it so that the phase residuals versus other spots have to be significantly below the target residual to be significant?
Yes.
And acceptable?
Yes.
And the target residual is just based on the background values or so?
Target residual is I think it's a combination of this theoretical value and the comparisons to other spots.
It's 8 and 8, and then the target residues are all. I would, if you remember, wasn't it so that you would have to compare the phase residual number versus other spots, the first one, with your target residual, and if you are quite better, then you can believe it, and if not,
yes. But actually, I always look at those values. I don't look at this. But I think having those two columns at quite low values is a good indication. This is another example. It's also a rather clear example, but we have different alternative series. So it's starting off with P2 here, which is a possibility. Then we have screw axis along B, and which is acceptable, along A, which is should be considered, and then we have actually a combination of these three. So we have a twofold perpendicular plane of crystalline and two times twofold screw axis in the A and B directions, and this should be considered. And generally, I think the philosophy should be to choose the symmetry, the highest symmetry on this. So in this case, definitely choose this one. And if you believe that your crystal maybe is a bit more asymmetric, so that you don't have this, you have one of these, you have to have very good data to prove that is really the case. So in general, choose the highest symmetry, which is indicated.
Maybe one of this, we changed this to guess that we actually favored the highest symmetry and is still accepted.
Okay, but that's, I think, the right thing to do. Yes. A tricky example. Do we have a couple of minutes? Okay. So this is from G, data on a putative potassium channel, and this is a tricky case because it's multi-layered and it has some additional difficulties. And these are the very low resolution spots shown here, and it could be indexed with a P321 lattice like this, but it could also be indexed on a asample CM lattice with absences here. 1, 0, 0, 1 would be absent. So every second spot would be absent in this symmetry here. So what is the correct lattice in this case? So these are projection maps now calculated in both symmetries, and you can see that we have a similar unit here of 3 proteins. So in the P321 case, there will be a perfect 3-fold symmetry here. In this position, so they would look identical. However, in CM, with the CM symmetry, there are no longer 3-fold axes here, and there will be some difference between those. Actually, there would be one which would be different from the other two. The other two would be related by a 2-fold screw axis in this direction, but this one would be different. And from processing and looking at a number of these and processing them in P1 and looking at them carefully, it's evident that CM is the correct assignment in this case, because one of them is different from the other two, and it also has a 2-fold rotation axis going right across the protein unit. So these are 2 layers on top of each other, so it's allowed. One could expect that to happen if it would have been a single layer. Of course, we couldn't have a rotation axis going right through the protein, but there are 2 layers on top of each other. But in the processing, of course, this creates a problem because this axis is unique, but it's very close to two other directions here, which are 120 degrees apart. So what she had to do was to index all of these images with three alternatives, and then during the merging process, select the ones which were correct, which had the axis along this direction. And in 2D, it's one can do it rather easily, but when it comes to 3D and these symmetries, as long as it's not tilted along this axis, the symmetry will gradually disappear, and it will be much more difficult, of course, to index correctly. So, very tedious work to index always every image in three alternatives, and then by looking at the merging residuals during the merging process, select the ones that were correct, and thereby gradually building up a 3D structure. So I think in some cases it might be difficult to automate completely, at least initially, the process. Once a reasonably preliminary 3D dataset is available, then one can proceed probably more automatically, but at least at the beginning, it's important to check what is really going on. I think this was my last.